Okay, and I just noticed I was getting a little more glare and I wanted on that light. I moved that light a little bit. Hopefully the glare is a little better. Okay, so we're talking about closed systems, and we said closed systems have a fixed amount of mass, no mass crosses the boundary. This is a common type of closed system we will encounter in this text and many other texts. This is what we call a piston cylinder. Right, piston cylinder. And what that means is that this lid right here can move up and down. So volume can change in a closed system. If I've got a gas in here, right, if I've got a gas contained in this piston, and I've got a very tight sealed lid up against the walls of this cylinder, and so this lid can move up and down in this cylinder, meaning the volume can change, but the mass is trapped in there. It cannot escape. And this is a common type of closed system we will encounter, is a piston cylinder, one where the volume can change. To change that volume, we're going to have to put energy into it, and we're going to talk about that later on. Okay? But this is a common example of a closed system, a piston cylinder, where volume cannot change. The other type of common closed system we will encounter is what we call a rigid tank. A rigid tank is a closed system where the volume does not change. But in a piston cylinder, the volume can change. Rigid tank, because the boundary is rigid and it does not move. In a rigid tank, the volume stays constant. Okay. Let's see here. Another type of control volume that we can see. Another type of system that we can encounter. As I said, two types of systems that we can encounter. The other one is what we call the control volume. Now, as you go on, let's start with the textbook definition. Textbook definition says a properly selected region in space. Now that is absurdly vague, right? Probably to the point of not being helpful. Control volume is where mass can cross the boundary. Now that's probably a little too specific, like in my fluid mechanics class, that's a little too specific. But for us in an introductory thermo course, that's really the main thing we need to come away with, is we're just going to select some region in space, right? I'm going to draw a system boundary around this cooling tower for an air conditioning unit. Okay? And this is a system. If this is my boundary that I've drawn here, mass is going to cross this boundary. You got to pop it in. Okay. We're going to have mass crossing this boundary, and that mass is going to come in the form of, you're going to have, if you stand next to one of these, you know you're going to have hot air coming out. And what it's doing is it's drawing warm air in through the sides, and it's using that air basically to cool refrigerant, right? It's heating the air up by cooling down the refrigerant. And what you also have, you'll see there's two little pipes down here. One of these is going to be in, one of these is going to be out, right? And so this one looks like it's out, and this one looks like it's in. So you've got, I'm not going to try to spell refrigerant down there, but you've got refrigerant coming in and going out. You've got air coming in and air going out through the fan. This is a control volume, right? Especially if I draw my system boundary right here. This is a perfect example of control volume that we would encounter. Now, there's a lot going on there we're not going to get into right now. We will actually in Chapter 6 talk about what's going on here. But for right now, that's sufficient. Okay? All right. This is Lecture 1 and 2. This is page 2. Can keep me organized there. I'm going to have a bunch of pages going here. Normally when I teach, I've got two big whiteboards, and I've got a projector screen in the middle with a smart board, and I would use all of it. And so it's look a little chaotic, but hopefully it's helpful. Okay. All right. So what's next then? Now let's turn the ink off, and what do we got Okay, so again, some terms that we absolutely have to talk about, as I mentioned in the previous video. I'm not going to talk about all the terms we need to in Chapter 1, we just don't have time, but some terms we absolutely have to talk about. Property. Property is kind of like a dimension. Property is any characteristic of a system, something that we want to measure. So again, like a dimension. Common properties that we're going to be concerned with right now are going to be temperature, pressure, and volume. And so those are three properties that we can measure for our system rather easily. Now, there are some properties we're going to deal with that are what we call intensive. That means they're independent of the mass of the system. Some properties are what we call extensive. That means they depend on the extent or the mass, how much material is present in our system. Now, for example, I've got a cup of water here. Okay, and as I said in the previous video, if I don't drink water while I'm talking for a long time, I lose my voice. So if I remove, so I've got a certain amount of mass in there. If I remove a small amount of mass from that, I have changed some of the properties. One property that I've changed is, give me my pen. Here we go. One property I've changed is the volume. Wow, I should write right-handed on these slides more often. Volume. Now, that depends on the mass or the amount present, the extent of the system. But one thing that doesn't change, there's several things that don't change, but here's the thing, the density. The density of the water in this cup, as I drink water out of this cup or remove water, change the mass, the density does not change. The volume does, the density does not. Volume is an extensive property. It depends on the extent or the amount of the system. The intensive property of density does not. It does not change as the mass changes. So it doesn't matter whether I'm talking about this small amount of water in my cup. It doesn't matter whether I'm talking about the gallons and gallons of water that's in the swimming pool. It's going to have roughly the same density. Right? And that's only going to vary as we change the temperature, but not the mass. Okay? Now, so three properties we could feasibly measure. Well, and these are what we're going to focus on today. And this is going to be kind of the focus of Chapter 1, is volume, we've just mentioned. Give me some ink, thank you. We've just mentioned volume. All right, so volume, number one. Temperature. Another one, pressure. So these are the three properties that we can feasibly measure for our system. Okay? So that's going to be our focus for Chapter 1. Now let's first talk about volume, density, and it's what I call density and friends. Okay? Density, volume, etc. All right, now this is how when I'm drawing in writing, I will draw capital V with a cross through it. That is what we call total volume. Okay? Now, this is what I do to distinguish volume. Why am I doing that? Well, here's the thing. So I'm going to keep on a separate sheet. What I would normally do is just, and you might even just on a separate sheet of notes, write these things. You're going to see these a lot, right? Volume. I put capital V with a cross through it. Okay? Now, why the cross? Because speed or velocity, magnitude of velocity being speed, we will use capital V with no cross. And this is how I will write speed, is V, so a sharp corner down here, sharp acute angle, same thing on this one, both of them have sharp acute angles. I will draw them fairly large, larger than my lowercase letters here, but if it's volume, I'll put a cross on it. If it's speed, I will not. Okay? So just so you know, again, keep have a separate sheet of notes, write these, and I'm going to add to them as we go. Keep those handy. I've got a sheet of engineering paper over here, just kind of off to the side. I've got on my floor down here. Here's another couple of things here. Now we've just mentioned density, which I will draw with a row. Right, that's how I draw my Greek row. You'll see why here in just a second. Most of the time, draw the lecture. So it's basically looks like a lowercase p with a backwards curling tail. This is my density. You want to just make sure it doesn't look like your p's. I put a backwards curling tail on it. That's what I do. Density, of course, being total volume per, density being mass per unit volume. Right? Mass per volume, mass divided by volume. That's density. Okay. Now, there is a lowercase v. So this is my lowercase v. I don't put the sharp angle I do on this one. This is a lowercase v, and make sure you draw it smaller than your capital letters. This is what we call specific volume. Specific volume is volume per unit mass. Volume divided by mass. Notice this is the reciprocal of density. If I know density, I know specific volume and vice versa. Okay? Now again, this is how I draw my lowercase v. So add to my list of things over here. I'm going to write it twice, that's okay. This is what we call specific volume. That is a lowercase v. Draw it smaller than the capital letters, and I draw, I don't put a sharp angle on the bottom of my lowercase v. Now a few other things here. As we mentioned, density, the way I draw it, kind of a backwards curling tail on what looks to be a P. Pressure, we're going to see that here in just a little bit. I draw pressure with a capital P, so no curl on the tail, and I try to draw it bigger than the other letters. Another thing that you will see, let's see, what was the other one I wanted to mention? That gets us for a bit, at least. Okay, I'm sure there's another one I'll think of here. Oh, yeah. Just to warn you, you will see internal energy a little bit later. That is a lowercase u. So this is how I will draw my u's. This is how I draw my v's. Anyway, you'll see more of that. But again, specific volume is volume per unit mass. Volume divided by mass, which we've already got there. So again, I've got a handy sheet. What the heck is Steve writing? Have that handy so you know when I write this random looking squiggle, what the heck is that? Okay. All right, let's see what else we've got here. Specific gravity. SG, you probably encountered in your chemistry class, maybe a physics class too. Specific gravity. Specific gravity is the density of your substance divided by the density of water. Right? And by the way, note for liquid water. And anytime I know it's liquid water, now don't, just because it says water, don't assume this. You need to know it's liquid water. Okay? If you know I've got liquid water, the density of liquid water is almost always about 1,000 kilograms per cubic meter, or in the English set, that's about 62.4 pound mass per cubic foot. Okay? All right. So that is density, and what I call density and friends. This density, specific volume, specific gravity. Okay. Now again, our goal here is we're talking about properties that we could feasibly measure for our system. Right? Those being volume, temperature, and pressure. So let's talk about temperature. Right? So what does it mean to be hot here? Oh, that's a good stopping place, honestly. Let's stop there, and we'll pick up the next video talking about temperature. All right, so pop here.